Hi everyone, in this chapter section we are going to talk about acid ionization constant. Please read the OER textbook for chapter section 14.3. The acid ionization constant Ka is the same as equilibrium constant K that we learned in Chem 122. The subscript A tell you that this equilibrium constant belong to an acid solution. Recall from Chem 122, the equilibrium constant expression K can be written as the concentration of the product raised to its coefficient and divide by concentration of the reactant raised to its coefficient. So that means in this case, the K value can tell us what happened at equilibrium. For example, if at equilibrium there are more of the product than the reactant, then the K value would be a lot greater than 1. It's suggesting that at equilibrium, the reaction lie far to the right, favor the product. Product is predominant. However, when you have equilibrium value that is a lot less than 1, that means that at equilibrium there are a lot more of the reactant than the product. So that means at equilibrium reactant predominant. That means that the reaction lie far to the left, favor the reactant. Note that the equilibrium constant K is not the same as the reaction quotient Q. Reaction quotient Q tell you about at any given point on the reaction. It doesn't have to be at equilibrium. However, K is have to be at equilibrium. But whenever that Q value equal to K value, we can conclude that at that point is already at equilibrium. But when Q is not equal to K, for example, when Q greater than K, it tells us that at that point of the reaction, there are more of the product than the reactant. So that means the reaction would shift toward the reactant to produce more of the reactant in order to establish the equilibrium. So that means in this case, the reaction would shift to the left. On the other hand, when Q is less than K, it indicates that at that point it's not at equilibrium. There are more of the reactant than the product. So the reaction would shift to produce more of the product until it reaches equilibrium. So to write the equilibrium expression for the acid is going to be the same as what I mentioned earlier. We're going to include the concentration of the product and divide by the concentration of the reactant, except we are going to exclude liquid and solid. So the Ka expression for this weak acid would be Ka equal to the concentration of hydronium ions multiplied by the conjugate base A divided by the concentration of weak acid. Since weak acid is only partially dissociated, so that means the Ka value of weak acid will always be less than 1. It's indicating that at equilibrium, the reactant is predominant and is only dissociated to give off only few hydronium ions molecules. As you see, the Ka is the ratio between the product versus reactant. So that means the larger the Ka value is tell us that it's going to give off more of the product, which are the hydronium ions and its conjugate base. So that means we can conclude that the larger the Ka, the acid will dissociate more into ions. So that means the acid would be a stronger acid. So that this is the reason why we can use the Ka value to determine the strength of the acid. Now let's take a look at example 1. Which of the following acid is stronger? Both of these acids are weak acid because their Ka values are less than 1. It indicates that these two acids did not dissociate well in water. That's why the Ka value are very small. In order to compare the relative strength of these two acids, we need to look at the value of their Ka. The higher value of the Ka tell us that it's dissociated more in water. So that means in this case, the higher value of Ka would be the stronger acid. So if you compare between hydrofluoric acid and hypochlorous acid, we can see that hydrofluoric acid has a higher Ka, so that means the answer for a stronger acid would be hydrofluoric acid. Next, let's take a look at example 2. What is the Ka of 0.1 molar formic acid that contains 4.2 times 10 to negative 3 molar hydronium ions? Before we can calculate for the Ka value, first you will need to write out the acid ionization of formic acid. The acid ionization in water of formic acid can be written as formic acid react with water, and because this is a weak acid, so we are going to use reversible arrow to indicate this. An acid transfer proton to a base water, so it's going to become a conjugate base formate ions, and the other species would be hydronium ions. So this is the acid ionization in water of formic acid. Then you can write the Ka expression for this acid ionization, which is going to be Ka equal to concentration of hydronium ions multiplied by the conjugate base and divide by the concentration of weak acid. So if you know concentration for each of these, you should be able to plug it in and calculate for Ka. The problem gives us that the concentration of weak acid, formic acid, is 0.10 molar, and the concentration of hydronium ion at equilibrium is 4.2 times 10 to negative 3 molar. If you think about this, whatever that the weak acid dissociate is going to give off 1-to-1 ratio between the conjugate base and hydronium ion. So that means if the hydronium ion has concentration of 4.2 times 10 to negative 3, the concentration of conjugate base would be the same as hydronium ions because the stoichiometric ratio are the same. Plug this concentration into Ka expression, you will get the Ka value of 1.8 times 10 to negative 4. Percent ionization is another way to measure an acid strength. The formula for percent ionization is concentration of hydronium ion divided by concentration of weak acid and then multiply by 100. It tells you that out of these, how much is dissociated to give off the hydronium ion. Let's take a look at example 3 for percent ionization. In order to calculate this, we will use the concentration of hydronium ion divided by concentration of weak acid, then multiply by 100, equal to 4.2%. This number tells us that every 100% of weak acid, only 4.2% dissociate. Therefore, we can conclude that for 0.1 molar formic acid, which is a weak acid, it has Ka value of 1.8 times 10 to the negative 4 and has percent ionization of 4.2%. Again, because this is a weak acid, it doesn't dissociate 100%. That's why the percent ionization is a lot lower than 100%, and the Ka value will be a lot less than 1. Example 4 is another type of problem that you will see on Newton homework. This problem again asks you to find percent ionization, give you the concentration of weak acid. However, it doesn't give you the concentration of hydronium ions, but instead it's giving you the pH value of this acid. You are going to learn more about what is pH in a later chapter section, but for now, please know that the pH value at equilibrium will tell you about the concentration of hydronium ion at equilibrium. To relate the concentration of hydronium ions to the pH, you can use this equation to solve for it. Concentration of hydronium ion would equal to 10 raised to negative pH if you plug this value in, you are going to get the concentration of hydronium ion equal to 0.01259 molar. Now we know both concentration of hydronium ion and also the concentration of weak acid. That means if you plug these two values back into the percent ionization equation, you should be able to obtain the percent ionization, which is equal to 8.39 in this case. If you compare between example 3 and example 4, the formic acid would be a weaker acid compared to this weak acid here, because this weak acid can ionize way more than the formic acid. Please practice more of this concept by doing the DIY that I provide here. You can also attend the hangout session to discuss with your peers and get help during the hangout session. The DIY key will be posted on Moodle after the hangout session. Thank you for watching.